I forgot to video me. And the electron withdrawing groups are going to be reduced. The electron donating groups are not going to be reduced. Because remember, electron donating groups donates electrons. A negative charge already has electrons. It doesn't want more. Electron withdrawing groups will stabilize electrons by pulling them away and making them more stable. So the question is, what do we have attached? We have a CH3 group. That's an electron donating group. So we will not get reduction here. And then our carbon-oxygen double bond, that is an electron withdrawing group because of induction. The oxygen is electronegative. And our lone pair isn't in conjugation with the pi bonds, so we can't donate electrons into the ring. So it's electron withdrawing group. So we will get reduction at that carbon. And then remember, our double bonds have to be opposite from each other in the ring. So there's only one way to draw this where we are not reduced, where we don't want to be reduced, and reduced where we want to, and that's here. So now the carbon where the electron withdrawing group is attached is being reduced, but the carbon where the electron donating group is attached is not. Therefore leading to lower energy intermediates. It's all about this intermediate. Any questions with that? Okay, so with the Frost circles, they're super easy. I'm never going to ask you to draw the actual p orbitals with these because it's too confusing. But the key is the point of the ring, one of the points have to be down. So the way I have it drawn, you can't just put lines and say this is our thing, because that's not right. A point's not down. So with the Frost circles, you just have to draw the ring with one of the points down, and then your orbitals are going to be at each carbon. So I like to redraw that so it's neater. So this is our orbital diagram, but we have to fill in our pi electrons. How many pi electrons do we have? We have 4. We have 2 electrons here, 2 electrons there, and this is an empty p orbital. So we have 4 pi electrons, but they are in cyclic conjugation. So we pair before we go to the next energy level, but then we don't pair until all degenerate orbitals have 1 electron in it. So what we end up with is an energy diagram that looks like this, and this is going to be anti-aromatic. We have that extra instability from the fact that our HOMO has 2 unpaired electrons in it. Remember, HOMO is highest occupied molecular orbital. If we're looking at these, first off, let's talk about our non-aromatic examples. The linear one, even though it has 2, 4, 6, 8, 5 electrons, it does make it anti-aromatic. It's just non-aromatic because it's not a cyclic conjugated system. It's a conjugated system, but it's not a cyclic conjugated pi system. So it's that linear system, it's non. The other non-aromatic system is this one, because even though we have a double bond here, it's not in cyclic conjugation, there's no p orbital. So that's also non-aromatic. We have to have a p orbital there. That other double bond is irrelevant to our aromaticity discussion. And then lastly, this one says it can't adopt a planar conformation. If it's not planar, that means the p orbitals can't be in conjugation, so then we cannot have cyclic conjugation. It's irrelevant how many electrons are there. If it can't be planar, it can't be aromatic or anti-aromatic. So now, looking at our other ones, does it matter that the benzene ring has this ring hanging off? No, as long as we have a planar cyclic conjugation series, it's going to be aromatic. So this has 6 pi electrons. The other thing hanging off the benzene is irrelevant. This is still an aromatic compound. Here, the question is, we have a total of 2 double bonds. We have a lone pair and a lone pair. So you might think this is 8 pi electrons, but these 2 electrons are not in the cyclic conjugated system because this p orbital is already full with this double bond. So that means these electrons can't also be in this p orbital. How many electrons can we have in an orbital? 2. So this orbital already has 2 electrons from this double covalent, well, this pi bond and the covalent bond. So these electrons are not in the p orbital, not part of the cyclic conjugated system. We don't count them. It is isolated or localized, as we say, to nitrogen. So this was a 2, 4, 6 pi electrons in a cyclic system, so it is aromatic. Those electrons aren't even in a p orbital, they're in a sp2 orbital. And lastly, this one, while these look similar, the difference is this one has this empty p orbital, so that means we have 3 p orbitals in cyclic conjugation. Our 4n plus 2 pi is what we're trying to get. That would equal to 2, because we have 2 pi orbitals, 2 pi electrons. N can be 0. So this is, in fact, aromatic. If you don't believe me, let's look at the frost circle. If I put the frost circle pointed down, I'll have 2 p electrons, and we do have that paired HOMO in lower energy. So we do have aromatic stability. But for that, we do have to have this to be an empty p orbital. That's not an empty p orbital, it's sp3. Then we won't have a cyclic system. Synthetic scheme here, we don't have any functionality. Well, we have the benzene ring, but there's not a lot of reactions that happen on the benzene ring, and we're not doing electrophilic aromatic substitution because we're not adding anything to the benzene ring. What instead we're doing is trying to put a bromine in one of the carbons, but we don't have any functionality there. But we can put functionality really easily in the benzylic position carbon by using NBS or Br2 in light. And when we do that, we're going to have some functionality. So that's going to be our most stable position, is going to be the benzylic position. So our bromine's still not where we want it, but we can easily make a double bond because one, if we put the double bond, if we do a elimination, our double bond is going to be in conjugation with the ring, so that's going to be a pretty stable double bond. Technically, you can use any strong base here, but it's best to use a larger strong base. Why? Why ethanol is okay, but this terpenoxide is better? Either position would be the most substituted. It doesn't matter. There's no other regio selectivity. The reason why the bigger base is better is that way we can make sure that we're not getting any SN2 possible. It's unlikely because it's tertiary, but just to make sure we can use a bigger base. But I didn't take off if you use the ethoxide or even methoxide here, but that can really help drive the reaction forward if we don't have any possibility of any substitution occurring. And then lastly, now that we have the double bond, we can put the bromine on the least substituted position because, of course, we can use HBr and peroxide. our anti-Markovnikov addition. So this wasn't a really difficult synthesis here. Now going on to chapter 19, actually, but quiz 9. Here we're actually, instead of looking at reactions occurring outside of the benzene ring in the auxiliary positions, we're looking at reactions occurring at the benzene ring, so our substitution reactions. So first off, we are substituting a hydrogen with a chlorine, so that's going to use our Cl2 and our AlCl3 to make it more of an electrophile. Then our next step, we have our chlorine. Our chlorine is now an ortho-para director, though it does make the reaction go slower. It is a deactivator, but because of the extra resonance structures, because chlorine does have long pairs that it can push into the ring in the our complex, our resonance complex, it is ortho-para directed. But para is going to be major. So I want the major, our minor because of sterics would be ortho. So our para is major. And of course, that's going to put NO2 onto the ring. Now, NO2 is a strong electron withdrawing group, so no reaction is going to occur with acylation and alkylation. Both of those reactions are just not electrophilic enough that once we put a really strong deactivating group on there that it's going to attack. So NO2, SO3H, pretty much just halogens are the only electron withdrawing groups that will still allow acylation and alkylation to occur for the most part. So we won't get a reaction. So here, first off, we want to identify what it's undergoing, which is really important. I'm making you do it here, but really any reaction you look at, you can think about these concepts. So our reagent is sodium hydroxide. Sodium hydroxide can either be a base or a nucleophile. But either way, it's not an electrophile. It's never an electrophile. So based on our mechanisms, we have two mechanisms where we use a nucleophile, and that is nucleophilic aromatic substitution and elimination addition mechanism. Both of those mechanisms, the ring reacted with a nucleophile. So that's our first key, is that this is a nucleophile. So clearly it's not electrophilic aromatic substitution, because that's when a ring is reacting with an electrophile. And this is not an electrophile. Now if we have a leaving group, which we have to have a leaving group in both nucleophilic aromatic substitution and elimination addition mechanisms, but if we have a leaving group where we have a electron withdrawing group ortho or para to it, then we're going to get elimination, we're not going to get elimination addition, because that benzyne ring is too unstable to push it to go through that. So it doesn't really matter as much the conditions, as long as, but 70 degrees Celsius is pretty low. So elimination addition wouldn't occur with sodium hydroxide at those low temperatures anyway. But as long as we have an electron withdrawing group, ortho or para to a leaving group, then the nucleophilic aromatic substitution is going to be a lower energy pathway, and we're not going to get elimination addition. What you have to understand is that benzyne ring is really unstable, so it's only going to go through that pathway if it has no other better pathways. So because we have an electron withdrawing group ortho to one of our bromines, we're going to actually get nucleophilic aromatic substitution. So we have two leaving groups. According to this bromine, the NO2 is meta to it, ortho meta. So the reaction won't occur at that bromine. But this bromine, the leaving group, the electron withdrawing group is ortho to it. So that's the leaving group where the reaction is going to occur. So even though the other bromine is going to be there, it's not going to go through that energy pathway. So I'm just going to label this BR1. Versus BR2. So that's where the reaction's going to occur. So now we're going to draw the mechanism of this. The other bromine's just going to hang around for the ride. Okay, so first off, we have an OH, it's a nucleophile. The nucleophile is going to attack at the position where the BR is. This is different from the benzyne mechanism. The benzyne mechanism, we deprotonate to form the triple bond. But the nucleophile is going to attack at the carbon where our leaving group is, and it's going to attack at at BR1, because BR1 is the one that has the NO2 ortho2. If it attacked at BR2, we'd never get that more stable resonance structure. That pushes the electrons onto the carbon. BR2 is just hanging out. Nothing's occurring at BR2. So that puts I just put a positive charge, it's not a positive charge. That puts our carbanion at that position. And let me draw out the NO2, because that's going to be relevant. So remember, NO2 always looks like this. The NO2 can really stabilize the lone pair by accepting the electrons, and then it'll have to push electrons onto the nitrogen. So that's one of our resonance structures. It still leaves that nitrogen positive though. And then of course, that's our extra resonance structure, that's our extra stable structure. This can only happen if our NO2 is ortho or para to that bromine. Because in the meta position, we can't push the electrons onto the nitrogen, making it more stable. But then we also have other resonance structures, of course, where the electrons can move around the ring. So pushing the electrons back into the ring. If we form the double bond here, that means that the lone pair pushes to that carbon. Have a good night. And I'm just going to write NO2 from now on. So now my lone pair is here. And again, this is a mechanism under OH negative conditions. It means we're only forming negative charge. Minus that positive charge on the NO2, that thing's always there. Doesn't matter what your conditions are on, that's what NO2 looks like. Then we can push the electrons again So now it's here. And then, of course, our last step, we're going to reform the aromatic ring. That's our electrons going here. And then one of those two things that's attached to this carbon has to leave to reform the aromatic ring. We have OH and we have BR. BR is a better leaving group, so it's going to leave, and that forms our final product. And of course, the OH won't take the place of this bromine because we won't get that extra stable resonance structure because NO2 is meta to that bromine. So that's not going to happen. So that explains why we need that electron withdrawing group, ortho or paro, to the leaving group. Any questions with that? I left off that resonance structure in here. I gotta fix that. Okay, now let's go through some synthesis. Now the synthesis isn't real hard here. We're pretty much doing a bunch of the same thing over and over again. The question is the order. That's a big thing. So with this one, there's two reactions that we're looking at, but the question is the order that we're doing it. So we can get that cyclohexane ring on there by taking benzene and reacting it with our alkyl halide and AlCl3, and that one's secondary, so that's fine for alkylation. Now this is going to be an ortho-para director, and major is para because of sterics. Our other option, or not our other option, but our other reaction is going to be putting the NO2 on the ring. So we just looked at that one. That's HNO3, H2SO4, and that NO2 is going to be meta directing. So we know we have to add the AlCl3 first and the alkyl halide because NO2 is ortho to our benzene, our cyclopentane ring. So if we add this first, that would put our ring in the meta position. Also, we can't do alkylation or acylation with NO2 group on there anyway. So NO2 group has to be after alkylation. So we know we have to do this first, followed by the second. The other thing is, once we put that cyclopentane ring on there, para is going to be major, but all we want is the ortho product. We can do that by using a blocking group. So we're going to have to do another reaction to block that para position. And the best for blocking is really the most useful thing the SO3H group is for, because it's easy to put on and it's easy to take off. And that can block that para position. And then it's easy to remove by using dilute H2SO4. So that's its usefulness. Now note, it is electron withdrawing, so you can't do acylation or alkylation once that thing's on there. But we don't have to worry about that because we're doing alkylation first. So we're going to do our alkylation first. We need our alkyl halide. You can also use the bromide and FeBr3, that's fine. There's no problem with that. I'm just drawing this particular one. Make sure you're not putting too many or too little carbons. That's a common mistake. We don't have any carbon spacers between the cyclopentane ring and the benzene ring, so don't put any extra CH2 groups in there. Now that we have this, it's an ortho-para director, but we want ortho, so we need to block the para position. So we're going to use our blocking group. That's going to direct to the para position and block it. Now we can add our NO2 group. And now, because the para position is blocked, only the ortho position will be available. But we don't want that SO3H in our final product, so we're just going to remove it with dilute H2SO4. You will get some minor ortho product, but if we want to get a decent synthesis, then we want as much of that ortho product as possible. So we want it to be major. We don't want it to be minor. That's where the blocking group comes in. Any questions? Okay, so for this one, we're actually putting 3 groups. So let's look at those reactions. Of our 3 groups, we are putting the carbon-containing group, but this carbon-containing group is primary, so we're going to have to do acylation followed by the reduction. Because if we form this carbocation, even in the presence of AlCl3, it's going to have the carbocation rearrangement. And what we're going to instead get is not the correct product. We're going to get this, and that's not what we want. So we want to do our acylation because of the carbocation rearrangement. So we can do acylation. One, two, three. I like to count my carbons for that one. It's an easy one to mess up. And of course, this is the acid chloride. We just were learning about the acid chloride. We still need the AlCl3 to make it more of a electrophile. Now, the acyl group is electron withdrawing, so this is a meta-director. Just keep that in mind. Then eventually we're going to have to reduce that. And this is the one that takes more energy, the zinc and mercury with HCl and heat. If we just use zinc and HCl, it's not enough to reduce it. So that gives us what we want in that primary position. And now this is ortho-para directing. The other reaction, we're doing NH2, but there's no direct route to put NH2. So instead, well, technically you can do elimination addition, but that's probably not the temperature that you want with the other functional groups on there. But what we can do is add our NO2 first. And then we can reduce that as well. And technically that just reduces with zinc and HCl. But if you use the harsher conditions to reduce the acetyl-1O, you're also going to reduce the NO2. So NO2 is meta-directing. And our NH2 is ortho-para directing. Then the last reaction we want to do, we want that bromine on there. So we can do Br2 and FeBr3. And our bromine is also ortho-para-directing. So those are our reactions we have to do in some sort of order. So to determine what order, first off, remember this has to happen before this, or this can happen after we reduce. But we can't have this happen after we put NO3 because we won't have that reaction. And a lot of people got it right on the first page and then still did the order wrong here. So that leads me to believe you're memorizing and not really thinking about what you're doing. So you want to think about it. So we cannot do acylation if we have that NO2 group on there. So we know that for sure. We know what we're doing there. So the question is where everything is. Sometimes there are multiple routes, but in this route, because if we do the bromine first, the bromine is ortho-para directing, but it's going to direct para first. So if we do the bromine first, then we have to add the NO2 first. And if we add the NO2 first, we can't do the acylation. We'd have to reduce NO2 to NH2. But if we reduce the NH2, it's going to do ortho. So we can't reduce NH2 first. So in this case, we can't really add the bromine first. The bromine will have to be last. Because otherwise, the only other option is adding the bromine first, using a blocking group, then doing the acylation, and then adding the NO2 after you remove the blocking group. And technically that probably would work, but it's a lot of steps. What you can do instead is you can do the acylation first. If we do the acylation first, notice, and I'm just going to put it where it is in the final product, but that's irrelevant really. Notice that the NH2 group is meta to it. So we can just add the NO2 next. We don't have to reduce it because this is meta directing, is going to direct in this position, and guess what's in that position? The NH2 group is in that position. So since we want something in that position anyway, we can just add that next. So that adds our NO2 in the meta position. Now NO2 is meta directing, and so is our acetyl-1O. But our bromine is para to NO2 and ortho to our carbon-containing group. So what we can do is we can reduce both groups now. Because if we reduce both groups, then they're going to be ortho-para directing, which is what we need anyway. Because we're reducing the C-double-bond-O as well, we want to use the stronger reducing conditions. If it's strong enough to reduce the C-double-bond-O, it's going to reduce the NO2. So that reduces both of those to the final groups that we want. Then we can just add our bromine. And the bromine is going to add in the correct position because we have a weak electron donating group, that's ortho-para, and then we have a strong electron donating group. So the strong electron donating group is going to win, so we're going to get para to the strong electron donating group because that one is going to win for the weak one. We do have a little bit of sterics in this position, but NH2 is pretty strong, so we'd expect that to win. So order here is really important. And sometimes that's the hardest thing with these, to make sure that the order works and it's going to direct in the right place, and we're not going to be doing a synthesis that goes through a reaction that's not going to happen, like acylation or alkylation after electron withdrawing groups are already on the ring. Any question with those? It's only like 5 reactions you have to know, but you do have to know how they direct and really think about the order. These are really like putting together a puzzle. If you like that sort of thing, don't do Sudoku, just do organic synthesis. Okay, so here we are looking at ketones and aldehydes. So naming. We want our parent to contain our aldehyde. Remember, don't number the hydrogen. That's not a carbon. So if our parent contains all of these carbons, we want our aldehyde, because that's our highest priority, to be the lowest numbering possible. The rest of the numbering system doesn't matter, as our aldehyde is taking priority. So the aldehyde, we just change it to Al. But we do have the double bond ene, so this is going to be an oct-ene-al. The al for the aldehyde, the ene for the double bond. And then the double bond starts on carbon 4. You can put the 4 before the oct or before the ene. You do not have to specify the number 1 for the aldehyde, because it's understood that aldehyde is number 1, because it has to be at the end and it has to take priority. So you don't usually see it. That's always right. For the aldehyde and the carboxylic acid, yes. If it's a ketone, it can be in the middle. So you do need to specify the locant. But the aldehyde and the carboxylic acid, they're always at the end. They never can be in the middle, so therefore they're always the lowest numbering system. So it's just not necessary. You don't have to put it, it's not common. Then we have 2 substituents. We have this butyl group at carbon 4, and we have the hydroxy group. Whenever there's a higher priority substituent, then OH is just a side chain. So B comes before H alphabetically, so it's going to be the hydroxy and the butyl first. And then, of course, we need the locant numbers. Hydroxy is on 7, butyl is on 4. Lastly, we do have a double bond. It is Z. You can play around. Of course, clearly, our highest priority is this group because H. And then here, you have to play around, but these are the same, these are the same. Your tiebreaker is these 2, carbon, hydrogen, hydrogen versus oxygen, oxygen, hydrogen. So this is your highest priority. So your highest priority is on the same side, so that's Z. And then we do have a stereocenter at 7, and that one's going to be R. 1 for OH, 2 for this, 3. I don't know why I just circled that. You don't typically circle the R. You can put the 7. You don't have to, because that's the only stereocenter. But you can. I don't take off if you do. Sometimes you'll see that specified as 7. But you don't have to specify it as 7. For B, we have 2 ketones. So remember, your parent cannot contain the carbon of the ring and a carbon of a linear chain. So our parent actually only contains these. We have 2 possible ways we can number these because we have 2 ketones. We want the lowest numbering system possible. So either we can number it 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Clearly, the lowest numbering system is going to be 1, 2, 3. So this is 1 and this is 3. The other route, your ketones are going to be on 3 and 5. That's a higher numbering system. We do have a longer carbon chain, but that doesn't contain our second ketone, so we don't want to use that one as our parent. So it's penta, and we have two ones, so one is for ketone, we have two of them, so dione. We do have to specify the locants for ketones because they can be anywhere, we don't know where they are. So we're on 1 and 3. You can put that before the parent, you can put it penta 1,3-dione, it's up to you. But you do need to specify where the carbons of the ketone are. Because they're in the middle, so they can be anywhere. Then of course we have a cyclohexyl group on 1, cyclopentyl group on 1, and a butyl group. I am just going ahead of myself and not thinking about what I'm saying. We have a propyl here, and we have our cyclopentyl. C comes before P, so propyl, and that's on 1, and cyclopentyl, and that's on 2. No, it's on 1 and 2. Sorry. Now technically carbon 2 is a stereocenter, but you can't assign it because I don't have the geometry specified, so you don't know what's coming forward or back. So we're just going to assume it's a mixture because it's not being specified. Okay, so looking at these, this diol under acidic conditions is going to react with a ketone or an aldehyde, but it's not going to react with our carboxylic acid too well. So we can utilize that under these conditions to protect our ketone or aldehyde and have no reaction occur with our ester or carboxylic acid. So that's what we're going to get, because as we talked about in the last chapter, the ester and the carboxylic acid are just too slow to react with those, and we don't get very much product. So what we're going to get is, now if this was an acid halide or an anhydride, that would be a different thing, but that's not the case.
So can you add the HSO4 first, then?
The H2SO4 is just protonating your oxygen of the ketone to make it more reactive. We're going to look at that mechanism over here. It's pretty much the same mechanism, except for in the one above, the diols are connected. Here they're not connected. But it's the same mechanism.
So you don't need to put numbers on
You don't need to put...
numbers on the both of them?
Oh, I don't know why I had that one there. That must have been an accident. I think I had like a 1 and a 2 for something else. Pretend like that one's not there. I changed things about my quizzes every semester, so I must have changed something there and just left that one by accident. But the one doesn't mean anything, it just means you mix them together. So the H2SO4 is just there to activate the ketone, and we're going to look at that mechanism in a couple of minutes anyway. So what we're reacting with is the ketone or an aldehyde, not the ester or a carboxylic acid. So we basically use this to protect, because it's really easy to remove this with a little bit of acid. So we have lithium aluminum hydride. We no longer have a carbon-oxygen double bond where the ketone was, so that means that the ester is going to be reacted. Remember, lithium aluminum hydride will react with that carbon twice to break this bond, because essentially the OR is our leaving group. I like to have numbers here. It's a lot easier so you don't lose carbons. So we do have 5 carbons there. So that forms this. And you don't need to put this, but I'm putting it just for clarity. The LAH means we had 2 additions of that hydride. So I'm drawing those 2 additions there. You don't have to put those 2 hydrogens. I'm just drawing it for clarity for when you're looking at it. And then that other group is on carbon 3. Now, If we just reacted this with H2O, we would retain that cyclic ether, but we reacted with H3O plus, that's going to remove the cyclic ether to reform the ketone. So that does happen when we react. It's really easy to remove this with concentrated H3O plus. So that's just done all in one step to both work up any LAH and protonate our OHs. This is our leaving group. And it also will reduce. We don't have to do a whole separate step to take that off.
So all these like bridges are just like blocking.
Yeah, the most useful thing for this particular reaction is as a blocking group. We call it a protecting group. And it's a good protecting group because it selectively reacts with the aldehyde or the ketone. Once it's here, we can't do a Grignard in this position. We can't do a reduction in this position. But then it's really easy to remove with a little bit of acid. Now what that means is, if we tried to do any reaction with this that pertained to acid, we couldn't do this because the acid would just remove it. But the Grignard in the reduction is under a basic condition, so it stays on. So it's a good protection group. A good protection group selectively reacts with the group that you want to protect, and then it's easy to remove to reform your original group. There's a lot more protecting groups out there. There's whole books on different protecting groups. We only learned about 2 protecting groups. The TMS group for alcohols and this group. But yeah, it's essentially blocking that position, making it unreactive to the other reaction. Okay, so here our amine is our nucleophile. We're going to lose water in this reaction. But we're starting with the secondary amine. So that means we'll have the 2 hydrogens to deprotonate. So we're going to form our carbon-nitrogen double bond. You should know this mechanism as well, even though we're not going through this one. If it was a secondary amine, we'd end up with a carbon-nitrogen, the carbon-carbon double bond. And this one's really well explained with the mechanism. That's Wolf Kishner. There we go. So, the main thing is, when we get to this point in the mechanism, if we started with a primary amine, we still have hydrogen available, so we retain that carbon-nitrogen double bond. If we start with a secondary amine, we no longer have hydrogen, so that means we have to deprotonate one of the adjacent hydrogens, because we won't isolate the nitrogen with positive charge very easily. The mechanism's pretty much the same until that part for these 2. And of course, OH is going to be a better leaving group as water, our OH+. So you should know those mechanisms, but these mechanisms are the same. And by know them, I mean understand them, not memorize them. Of course, you do have a lone pair there. And it should be bent. I didn't really draw it the right way. I'm supposed to draw that nitrogen as bent. There we go. Here, there's actually 3 routes that we talked about to do this. To completely reduce the carbon to an sp3 carbon with all hydrogens. 1, we just talked about. HCl. And heat and zinc and mercury. Or we can use something similar to our protecting group, but instead it has the thiols with the presence of H2SO4, and then treat that with Raney nickel. That's another route. Or we can react it with hydrazine. That will give us an intermediate like this, but instead of this being a cyclohexane ring, it's NH2. And then under basic conditions, which of course has to be done second because you can't really react H2SO4 in the same thing as NaOH. What we'll do is form into gas, which is a driving force of 2. I would have accepted any of these. Those are 3 routes to fully reduce the carbon-oxygen double bond.
Even if it's attached to a benzene ring?
Yes. It'll reduce the, in fact, they all work if it's attached to benzene ring. The HCl, heat, and zinc and mercury work a little bit better when it's attached to benzene ring, but all 3 of these routes would work. And I would accept any of them for this answer. Here we have our oxidation where an oxygen is going to be inserted into between the carbonyl carbon and the R group to form an ester. The question is what's going to be inserted. So H is the easiest thing to move because it's small. Then our tertiary because it's more electron donating. Then our secondary because it's not as electron donating as our tertiary. And our benzene ring is about equal with secondary. If we have a benzene ring on one side and a secondary on the other, it's going to be a mixture. Because while secondary isn't as electron donating as phenyl, phenyl is bigger, so it's harder to move. So this is looking at size and electron donating ability. Then primary and lastly methyl was our least electron donating, but still pretty big compared to hydrogen. So we have a tertiary and we have methyl. Tertiary is easier to move, so it's going to insert between the carbon-oxygen double bond and the tertiary carbon. And then you formed an ester. For the Wittig, we're reacting the alkyl halide, and what happens is the alkyl halide is going to react with the triphenylphosphine in the presence of this really strong base to form that iliad with a carbon phosphorus bond. It works best if the alkyl halide is least substituted because the triphenylphosphine is really big. So one of the carbons of this double bond is going to be the alkyl halide carbon, and one of the carbons is going to be the carbonyl. But we want the least substituted carbon to be the alkyl halide. The other thing is don't lose your carbons. So this will be the alkyl halide because this one's least substituted. But it's really easy for this one to lose a carbon. So that's 1, 2, and here's my chlorine. And then the other carbon is going to be a carbonyl, a C double bond O. Remember, your total carbons should be, in your final product, this plus this. So if you add the amount of carbons here plus the amount of carbons here, and you have more or less, you lost or you gained the carbon that you should. You shouldn't have more carbons in your product than your 2 starting materials combined. So technically this could work with a secondary alkyl halide, but this is the better route with the least substituted. If they're both equally substituted, then either route will work, just as equal. But you want your alkyl halide to be least substituted because it will work better. Okay, let's look at that mechanism. Now this mechanism is pretty much the same as, or if I was doing the protecting group mechanism, it would be the same. Also, if I was doing this with the thiol, it's pretty much the same mechanism as well. The only difference is we're going to have two additions of this OH. Now, first off, the first step is it's acidic conditions, so we're going to activate the oxygen. Acidic conditions, we're never going to form a strong negative charge because a reactive negative charge, a strong base, will just react with H2SO4. So it's unlikely to form just because of those concepts. So that means that with H2SO4, we're never going to form an O negative because alkoxides are very strong bases. Not strong bases, not as strong as like a carbon with negative charge, but a pretty strong base. So we're not going to form any oxygens with negative charges. Definitely no carbons with negative charges. So I keep on seeing this. I see this often, and it's incorrect because a couple of things. The first step is going to be a proton transfer to where you are making the oxygen a positive charge, but the proton is not coming from our alcohol. Why? This isn't right. First off, if the proton was coming from your alcohol, you'd form an alkoxide, which is very unstable in acidic conditions. But second, let's look at the pKa. The pKa of OH is about 16. The pKa of our hydrogen in H2SO4 is something like -9 or something. I don't know, it's crazy acidic. Why would a sort of basic oxygen, but not very basic oxygen, deprotonate an alcohol over a strong acid? Your source of proton is coming from the H2SO4. It is not coming from a neutral alcohol. Acidity-wise, that makes no sense. Oxygen is not, a neutral oxygen is not strong enough to deprotonate an alcohol. So the source, while this first step is basically what's happening, it's not coming from the alcohol. It's coming from our H2SO4. And I don't mind if you just put H+, because H2SO4 is a source of H+. H3O+ is okay. H2SO4 is dissolved in some water. But it coming from the alcohol is wrong, because the alcohol is not that acidic. It's all about your pKa's. So you do form this intermediate. Now we have our carbonyl carbon is going to be more susceptible to attack because we lowered, well, basically we made this reagent higher in energy. So that means that our OH is going to attack it more. And it's going to attack as a neutral alcohol because, again, we will not form an OH negative in this reaction mixture. So it's going to attack carbonyl carbon, pushing the electrons onto the oxygen. You can kind of think about your oxygen as a leaving group, even though it's not leaving, it's taking the electrons, and it's taking the electrons to be neutral, so that makes sense. Now, with a full mechanism, we need to show this OH being deprotonated, because, yes, eventually, we're going to protonate this alcohol to make it a good leaving group, but it's really unlikely that we'd have two protonated oxygens in one compound, because remember, compounds don't want to have multiple charges. So we're going to show this proton transfer to be really clear with this mechanism. There's a couple of things that could be deprotonating this. One of the alcohols could deprotonate this. You can just show water, which is of course in the reaction mixture because H2SO4 is going to be dissolved in some amount of water, deprotonating this. Unlikely that the conjugate base of H2SO4 is deprotonating it, but you can kind of show that as well. But something is going to deprotonate this to make it neutral. So now we have one of those on there. But our final product has 2 of these. And also, all of these steps are pretty reversible. Just, in my mechanism, I don't really take off for you not putting the reverse arrows, but they're all pretty reversible. We're using concentrated H2SO4 to drive the reaction forward. So then we want a second attack of our I gotta fix that. Of our alcohol, but what's gonna have to happen is we need a good leaving group, and that leaving group is gonna be water, but it's not gonna leave as OH minus. So again, we have to have another proton transfer. So we're gonna do H plus. I'm not gonna keep on drawing the H2SO4. It's not really even necessary. Now we have a good leaving group. Now we're not going to get the SN to attack at a tertiary carbon, a sterically hindered carbon like this. So what's more likely is we're going to reform the carbon-oxygen double bond, pushing off water. This is going to give us much more room for the second attack, sterically. That does leave a positive charge on that oxygen. Because oxygen, when it has 3 bonds, it has a positive charge. Then, our neutral alcohol could then attack again. In the case of the protecting group, it would be already attached. But in this case, it's a second mole of ethanol, or isopropanol. So we get that attack that pushes the electrons up. We're almost done. But that attack neutral, so that's going to leave us with a positive charge. So our last step is just one last proton transfer. And of course this lost water. One last proton transfer to form our neutral product. And again, water is being formed in the reaction, so it's likely water. Notice no negative charge is being formed in this reaction, with the exception of our conjugate base of H2SO4. But that's what makes H2SO4 such a strong acid, the fact that its conjugate base is stable. So that has to form. But no strong bases can be formed in the presence of acidic media. So a bunch of proton transfers typically happen. The other key is this step. You might be tempted to have your second alcohol attack and push that off in an SN2 reaction. Remember, SN2 reactions don't occur as sterically hindered carbons. So instead, it's much more likely that this trinoplanar carbon reforms, and there's a lot more room sterically for the attack at this position. Any questions with that mechanism? The mechanisms for today's quiz is also very similar to this. And as for a synthesis for this one, there's actually 2 routes for this synthesis, and they're both good. But the first key is either route that we take, forming a new carbon-carbon bond, we have to protect that ketone. If we make a Grignard, which we can easily do, we have to protect that ketone because Grignards react with ketones. That's what we react Grignards with, carbon-oxygen double bonds. Our other route is we can do a Wittig, but again, our Wittig reacts with a ketone, so we have to protect the ketone either way. So our first step with either route is protecting the ketone, because once we make a Grignard, once we make the Iliad of the Wittig, it'll react with itself or another molecule of itself, and then we're going to have a big mess. So we have to protect that ketone, so we can do that under both routes. And we just went over pretty much the mechanism for them. So now that we've protected it, we can do things now. So first, here's our new carbon-carbon bond between carbon 5 and carbon 6. So we're adding 3. So there's 2 routes we can go about it. Let's look at the Grignard first. So with the Grignard, we already have an alkyl halide, so all we have to add is magnesium. And then we have a Grignard. We don't have to do anything else. So we need to react that Grignard with a ketone that contains carbons 5, 6, and 6, 7, and 8. Here's carbon 6, 7, 8. So here's our ketone, followed by, and in this case I'm just going to use water. I'm going to try to retain that protecting group just so I don't have any side products that I don't want. So you have to be a little careful with your conditions that you're retaining this protecting group. And that might be a little tricky in the lab. Now this does leave an OH. But now I have my right amount of carbons. Because remember, when your Grignard attacks, we leave that alcohol. But we can form the double bond between 5 and 6. We just need the most substituted double bond, which is pretty straightforward. But we do have to make OH a good leaving group. So 5 and 6 would be a tri-substituted. A double bond between 6 and 7 or 6 and 8 would be di-substituted. So if we want our most substituted, we can use our strong small base. But first we need to make alcohol a good leaving group. We can do that by using tauset chloride. And then this. That will give us our double bond in the position we want. And the last step is to remove the protecting group with some water. So dilute H2SO4. Is it likely that protecting group's still there? You have to be really careful to keep it there, but and it might not even necessarily have to be there, but if we have the ketone and we have this strong nucleophile, we might get it attacking the ketone. So that's why we want to try to keep it on there. Now that's one route. The other route is the Wittig route. So in the Wittig route, we just need to react our alkyl halide with that really strong base, the butyl lithium, and then react it with our triphenylphosphine. And then we can just throw in that ketone, same one that we would have used for the Grignard. And that forms the double bond between 5 and 6, because that's what the Wittig does. And we already have the alkyl halide in the least substituted position, so that's really nice. And then all we have to do is remove the protecting group. Both routes work. But the key step is you have to protect the ketone first for either route. The first route had a little bit more steps, but butyl lithium can be rough to work with, so you might want to avoid that. So both routes can work. Okay, lastly, any questions there before we go to the quiz from today? Lastly, the quiz from today. A little bit of naming. We have a benzamide. That's just the amide from the benzoic acid. So our amide directly attached to our benzene ring. And then we have two ethyl groups attached to the nitrogen of the amide, hence the NN, and they're ethyl. So 1, 2. Okay, for the second one, I think it's easier for this one just to name the carboxylic acid first and then change what you need to, which is going to be changing the ic acid to YL chloride, or YL halide, but we have a chloride, so it's YL chloride. So for this one, our carboxylic acid, which was, remember, all of the derivatives are named based on what the carboxylic acid was named. So benzoic acid is this. So benzamide would look like that with the amine, with the nitrogen. So all of these are named based on the carboxylic acid names. So the carboxylic acid for this one, the carboxylic acid is directly attached to a ring. So when it is directly attached to a ring, we name the cyclopentane ring. And then it's just cyclopentane carboxylic acid. So that would be the carboxylic acid name. Actually, carbonic acid, not carboxylic acid. And then to change it for the acid chloride, the ic acid changes to our YL halide, in this case chloride. So it's going to be the cyclopentane carbonyl chloride. And remember, this carbonic acid is only when the carboxylic acid is directly attached to a ring. If it's not, then you just name it following the route we're going to do under it. So naming this based on the IUPAC naming is going to be a pentanoic acid, but we have two acids, so it's a pentane dioic acid because we have two of them. Now we don't have to use the locant numbers necessarily to represent where the acid is because we know the carboxylic acid is going to be at the ends. But we do have a substituent, the cyclobutyl. So the cyclobutyl is just a normal substituent. But we do need to specify where it is. We can name either of the carboxylic acid carbons 1, but we want the lowest numbering system possible for the cyclobutyl because it doesn't matter which numbers our carboxylic acids are. Now if our carboxylic acid we only had 1, that would always be number 1. But we can number it 1 and 5. So we want the lowest numbering system, so that'll be the one where our cyclobutyl is on carbon 2. Now you don't need to name 1,5 for the pentane dioic acid because it's understood that it's at the ends of the parent chain. Then the last step, this is S. Of course, this is our number 1 carbon. It has the highest priority. Because it's attached to, this is carbon, 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 we have a 3-way tie. And it's attached to oxygen, 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 so that's clearly linked. Here, these two also have a tie. We have carbon, carbon, hydrogen versus carbon, hydrogen, hydrogen. So this is 2 and this is 5. And it's coming forward. So that means our number 4 is going back. So this is S. We're making the anhydride. There's 2 routes. You can either heat it to 800 degrees Celsius. Not the best route for most cases because it's really hard to heat stuff to 800 degrees Celsius. Plus, that temperature can degrade the other stuff. The other route is you can deprotonate the carboxylic acid by using sodium hydroxide and then react it with an acid chloride containing the R group that you want for your thing. Our R group is, let's say this was our original one, which is irrelevant, but let's say it is. So the R group that we want is this. R bromine, but chlorine's the more common. So that's a good route. Or heat, but like I said, heat's not usually the best route. So now we're going to, we have a symmetric symmetric anhydride that's really useful. Our nucleophile is the electrons on the nitrogen. So we're going to attack one of the carbonyls, which is going to, and this is not the full mechanism, going to result in the loss of this leaving group. The bond is between the nitrogen and the carbon. We have those three. And we will have the deprotonation of one of the hydrogens. Remember, nitrogen is neutral when it has 3 bonds, so it does retain one of those nitrogens. And then, of course, and I didn't take off if this was here or not, but you also formed this leaving group. I didn't take off whether that was there or not. But that's our leaving group. It's stabilized by resonance. Here, I already gave you it's MgBr, so you know it's a Grignard. But the key is we have an extra carbon. We form the carboxylic acid. So we can do that by reacting it with CO2, followed by a little bit of acid, and that's going to form the carboxylic acid. And that adds that extra carbon. This is carbon 2. Remember, I do need that 1 and that 2 there because you cannot do a Grignard with H3O plus present. Now, if I didn't have the magnesium there, if I just had the alkyl halide, you could also react with, but I did have the magnesium. But you could also, if I didn't have the alkyl halide, react with cyanide and then use acid or basic conditions to form the carboxylic acid as well. But the cyanide won't react with the Grignard reagent because the Grignard's a nucleophile and the cyanide's a nucleophile. So cyanide won't do anything in this with this starting material. But if I didn't have the magnesium there, you could technically do that. That's another route that would also add a carbon. C is not a simple lithium aluminum hydride reaction because we did not reduce the ketone. We selectively reduce the carboxylic acid without touching the ketone. So this is not just a simple lithium aluminum hydride. We can use, we learned BH3 with THF to do this, and that will selectively reduce the carboxylic acid and not the ketone. Or the other route, which I accept if you chose, was we can protect the ketone. We just went through this from the last chapter, followed by the reduction with lithium aluminum hydride, and then followed by removal of the protecting group. I would accept that. Or you can just use BH3THF. But we just went through a quiz where we talked about that. And that route would work as well. Or we protect the ketone and then selectively reduce the carboxylic acid. So either route would work. So Dibol, that is one of our poison hydride agents. It has those 2 big bulky all groups. So we're only going to get 1 addition of hydride. So that means we're going to form an aldehyde, and then our oxygen is a leaving group. Again, numbering here is really useful. That's a 1. I don't know what happened. So of course, that ester is now that OH, and then we got only one addition of the hydride. If we use lithium aluminum hydride, we get two additions. And we'd have the alcohol, the primary alcohol. Okay, so number E, we have an acid chloride, and we formed a new carbon bond. But notice, we only have one addition of that bond. So this is not a Grignard, because a Grignard would add twice. So we'd have two new carbon bonds, and we'd end up with an alcohol. So the reagent that will add once to an aldehyde, once to a acid chloride or an anhydride is the Gilman. So that's your R group attached to CuLi, but it's two of your R groups because that's the way copper binds. Now be careful here, don't add too many carbons. I don't know, what is that? And we have two additions of those. Or not two additions, we have two of that same R group attached to copper. But it only adds once to either the acid chloride or the anhydride. And you get the same answer with the anhydride. It's just sometimes the anhydride is easier to work with. Okay, here, because the oxygen is going to be a better leaving group than nitrogen, we're going to reduce, but we're going to reduce to the amine where we won't have the oxygen any longer in our structure. So we don't have any change in the amount of carbons. All we do is have a change in the hydrogens. Here. You don't have to show the hydrogens. I'm showing it for clarity when you're going back and looking at it. And again, looking at that mechanism, you see the oxygen's a better leaving group than nitrogen. So in most of our reductions, we lose the other leaving group, but here, the leaving group is the oxygen. Okay, so this particular synthesis mechanism is very much like the mechanism we showed before. But we have this leaving group. Again, it's acid catalyzed, so again, the H plus source is coming from our acid, our H2SO4, not from the alcohol. We don't form negative charge, a strong base in a acidic media. So our H plus is coming from our H2SO4. You can draw the H2SO4, but I'm just going to draw H plus. So our first step, just like our mechanism we saw earlier, is going to be protonating our oxygen to make it much more susceptible to attack. Now that we have that positive charge, now our methanol can attack, and it's going to attack neutral. That's going to quench that positive charge, but then we're going to end up with a positive charge on the oxygen of methanol. It's very similar to the mechanism from before. Don't forget your formal charge. Now before we go anywhere else, we're going to have a proton transfer to neutralize this compound. Again, you're doing this in catalytic amounts of H2SO4, so that means you have some water present. So I can assume water is deprotonating. You could also show the methanol deprotonating. But when the water deprotonates, it just forms H3O+. Remember, we'll often show acid as H3O+. So we're going to be opening up the ring, which means the oxygen of the ester is going to be leaving, but it won't leave as a negative charge. So we're going to have a proton transfer, and again, all of these steps are pretty reversible. Again, we have H plus all over in this reaction because that's the conditions, is acidic conditions. So we can get the protonation. Now that's going to make that oxygen a pretty good leaving group. We're going to reform the carbon-oxygen double bond. And like I said, this is a good leaving group now. It's going to leave neutral. Again, we're not forming any negative charge. I'm just going to rearrange where this OR is, but I didn't change anything. So the last step, we're not going to isolate the oxygen with a positive charge. So again, there's water floating around. So we're just going to have that proton transfer. Form the neutral compound. Oh, let me put this in blue. So you can see where the methanol came in. So very similar to the mechanism of before. But we retained the carbon-oxygen double bond because we had a good leaving group. Whereas in the other mechanism, we didn't have a leaving group, so we had those two attacks. Any questions? Lastly, the ones from today. So the Grignard is going to attack the carbon, but then we're going to form a carbon-oxygen double bond at that carbon. It's a little bit different with the nitriles. The nitriles, the only ones that are different. So I'm going to label this as 1 and 2. So here's my new carbon bond. And my carbon-oxygen double bond is going to be on 2. And that carbon-oxygen double bond comes from when we react the H3O+. The carbon-nitrogen double bond is there until that step. And then our synthesis. This one is a couple of steps. But don't try to jump to forming the amide. Remember, you can form the amide through an acid chloride or an anhydride. And you can form an acid chloride and an anhydride through a carboxylic acid. So that's easy enough. So think about that last. And let's ignore it for now. First off, what I want you to notice is that we have an extra carbon. Well, we did this reaction earlier. If we take this and we make it a Grignard, and then we react it with CO2 and H2O, or H3O+, we're going to form the carboxylic acid with the new bond. Carbon 3 is coming from our CO2. The other route you could take for this one is to take your sodium cyanide, do an SN2 reaction, that also gives us that extra carbon, and then we can form the carboxylic acid by using H2SO4 hydrolysis. Now these are rough conditions, or sodium hydroxide hydrolysis. So we looked at both of those today. They're both kind of rough conditions, but we don't have any other functionality, so it can work. The step here, though, that's a little dangerous is the cyanide. But both routes work to get to the carboxylic acid. Once you form the carboxylic acid, we can't just react this with NH2CH3 because it's really slow. The amide doesn't react real well with the carboxylic acid, but it does react really well with an acid chloride or an anhydride. So if we take our carboxylic acid and react it with SOCl2, we can form the acid chloride. Once we have the acid chloride, we just need excess of our NH2CH3. There's our nucleophile. We want excess because the extra nitrogens can act to depropane. Or we can take our carboxylic acid, react it with sodium hydroxide, and throw in the acid chloride. Now, I don't know why you'd have this acid chloride sitting around, but let's say you did, because this is a kind of complicated acid chloride to just have sitting around in the lab. Like, you probably couldn't purchase this one. You might be able to, but it's unlikely. But let's say you did have it sitting around and you didn't have to make the acid chloride. Then you can form the anhydride. And we want that symmetric anhydride. And then again, we can react that with H2NCH3. No, it would make 1 plus the leaving group, OH, which you have to remove. So that's a byproduct, and that might be an issue with this one because you might not have that well solubility. So that in this case, because this R group's kind of complicated, this might not be the best route. The acid chloride might be a better route. But I would have accepted either. Any questions?
You say majority of this exam is mechanistic stuff.
I always have, no, usually the majority of the exam is one-step synthesis. I think that's like 36 points. I always have a naming section. In this case, we're going to have a section deciding aromaticity, circling, boxing, leaving room. There's going to be a single-step synthesis where we fill in the boxes or the products or whatever. And that's usually a pretty big percent because we have a lot of those.
Okay, so
And then synthesis. I think the mechanism section, I mean, you need to know your mechanisms. If you don't know mechanisms, that's an easy 15 points you're not going to get on the test. And then I have a little bit of miscellaneous questions, like maybe explaining aromaticity using frost circles, or maybe looking at things like explaining reactivity of the different derivatives, things like that. And then, of course, there's always a bonus. It all adds up, but the one section that usually is worth the most points is single-step synthesis of any of the tests I do. But you can't really just skip mechanisms.